most dangerous moment in human history happens in silence. I have spent 3 years calculating the mathematics of nuclear fission, designing the mechanisms for controlled detonation, solving the engineering problems that would make atomic weapons possible. But nothing in physics prepared me for what I witnessed at 5:29 inches the morning on the 16th of July, 1945, in the New Mexico desert. Most people imagine nuclear explosions as noise and destruction. They think of Hiroshima photographs, mushroom clouds, the thunder of war. But the first nuclear detonation began with something far more unsettling. For the first 2 seconds, the most powerful explosion in human history was perfectly, completely silent. Light without sound. A flash brighter than the sun at noon, bright enough to illuminate mountain peaks 10 miles away, bright enough to feel his heat on your face from 20 miles distant. And in that silence, watching the birth of atomic fire, I understood that we had not simply built a weapon. We had crossed a threshold in physics that changed what it means to be human on this planet.
Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next.
The path to that silent dawn began with equations on a blackboard at Berkeley in 1942. I was teaching quantum mechanics to graduate students when General Groves first approached me about what would become the Manhattan Project. At that time, the theoretical possibility of nuclear fission had been established for only 3 years, since Hahn and Strassmann's work in Berlin. The mathematics were elegant, almost beautiful in their simplicity. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits, releasing enormous energy and additional neutrons that can split more nuclei. On paper, the chain reaction looked manageable. We calculated critical mass, estimated yields, drew diagrams of implosion mechanisms. I filled notebook after notebook with equations predicting exactly how much energy would be released when we compressed plutonium-239 to supercritical density. The numbers were precise. Each fission event would release roughly 200 million electron volts. With 13 pounds of plutonium and perfect compression, we predicted an explosion equivalent to 20,000 tons of TNT. But numbers on paper carry no weight, no heat, no light that burns your retinas 20 miles away. In my Berkeley office, surrounded by textbooks and academic journals, the theoretical energy release seemed like an abstract concept, no different from calculating the binding energy of any other atomic nucleus. I understood intellectually that we were designing a weapon of unprecedented destructive power. But understanding mathematics is not the same as witnessing physics become reality. The Los Alamos laboratory transformed me from a theoretical physicist into something else entirely. When I accepted Grove's invitation to direct the scientific effort, I thought I would be solving an interesting problem in applied nuclear physics. I had no conception of how the work would change, not just my understanding of the physical world, but my understanding of what it means to hold such knowledge. My colleagues and I spent months refining our calculations. Enrico Fermi worked out the neutron diffusion equations. Edward Teller explored fusion possibilities. Hans Bethe calculated energy yields with extraordinary precision. We built computational models, constructed test assemblies, measured cross-sections and reaction rates. Every day, our theoretical understanding became more sophisticated, more accurate, more complete. Yet something troubled me even then, though I could not articulate it clearly. The mathematics predicted that our weapon would release energy equivalent to a small earthquake, but equations cannot capture the full reality of what such energy release means. When I calculated that our bomb would create temperatures exceeding 10 million degrees Celsius, I understood this as a number. I knew it was hot enough to ionize any known material, hot enough to replicate conditions inside the sun. But I did not truly comprehend what it would mean to create a piece of the sun on Earth. The theoretical work consumed us completely. We lived and breathed fission cross-sections, neutron multiplication factors, implosion dynamics. I would wake in the middle of the night with new ideas about lens design or tamper materials. My mind constantly returned to the central challenge: how to compress plutonium symmetrically and rapidly enough to achieve supercriticality before the chain reaction blew the assembly apart. The calculations suggested we needed explosive lenses arranged in a perfect sphere around the plutonium core. The timing had to be precise to within microseconds. The compression had to be uniform to within fractions of a millimeter. Any asymmetry would cause the plutonium to squirt out sideways instead of compressing to critical density. The mathematics demanded perfection that seemed impossible to achieve in practice. As 1,000
1,944 progressed into 1,945, our theoretical predictions grew more confident, but so did my apprehension about what we were creating.
The equations told us our weapon would work, but they also told us it would work better than anyone had initially imagined. Our early estimates of energy release kept climbing as our calculations became more sophisticated. What started as a prediction of equivalent to a few thousand tons of TNT grew to 20,000 tons, then more. I began to understand that we were not simply building a larger conventional explosive. We were accessing a fundamentally different source of energy, the binding force that holds atomic nuclei together. In chemical explosives, energy comes from rearranging molecular bonds. The energy per molecule is measured in electron volts. In nuclear fission, energy comes from rearranging nuclear structure. The energy per nucleus is measured in millions of electron volts. The difference in scale was not incremental, but revolutionary. The final months before Trinity were consumed with engineering challenges, but the mathematical foundation was solid. We knew our weapon would work. The question was no longer whether it would detonate, but whether we were prepared for what would happen when it did. The equations predicted light intense enough to cause temporary blindness, heat capable of igniting materials at considerable distances, and a shockwave that would shatter windows dozens of miles away. But equations, however accurate, remain abstractions until they encounter reality. I understood this intellectually, yet still I was not prepared for what I would witness on July 16th. The mathematics had predicted an explosion, but mathematics cannot predict how it feels to watch the birth of atomic fire, to see theoretical physics manifest as a force that illuminates mountain ranges and turns sand to glass. In those final weeks before the test, I would sometimes hold the calculation sheets in my hands and try to grasp their full meaning. These pages, covered with differential equations and numerical estimates, represented the accumulated knowledge that would soon become the most destructive force ever unleashed by human beings. The neutron multiplication factor, the critical mass calculations, the yield predictions, all of it was about to be tested against reality. I remember thinking that once we crossed this threshold, there would be no returning to theoretical speculation. The genie, as the saying goes, would be out of the bottle. Our calculations would no longer be academic exercises, but the blueprint for weapons that could level cities. The abstract mathematics would become concrete policy, and I would bear responsibility not just for solving an interesting problem in nuclear physics, but for fundamentally altering the nature of warfare and perhaps human civilization itself. The weight of that responsibility pressed on me more heavily as July approached. I had entered this work believing that defeating Nazi Germany justified any means necessary. But by 1945, Germany had surrendered, and still we pressed forward toward our test. The mathematics that had once seemed like pure science now felt like a burden I would carry for the rest of my life. The Jornada del Muerto, the journey of death, stretched before us like the surface of an alien planet. Spanish conquistadors had named this desolate expanse of New Mexico desert centuries ago, recognizing it as a place where men could easily perish from heat, thirst, and the sheer emptiness of the landscape. When General Groves and I first surveyed potential test sites in 1944, the irony of the name was not lost on me. We were indeed embarking on a journey that might lead to death on a scale previously unimaginable. The site we selected lay 200 miles south of Los Alamos, far enough from populated areas to minimize immediate risk, yet close enough for our team to reach by automobile. The Alamogordo bombing range offered 18 miles by 24 miles of restricted airspace and relatively flat terrain. More importantly, it was already under military control, which simplified security arrangements for what would become the most classified experiment in human history. Standing in that barren landscape for the first time, I tried to imagine what would happen here. The calculations predicted a fireball several hundred yards in diameter, temperatures that would vaporize any known material, and a shockwave powerful enough to knock a man to the ground at considerable distance. But the desert around me seemed too vast, too ancient, too permanent to be transformed by anything humans might create. We began construction in late 1944, building a small city in the wilderness dedicated to a single purpose. Base camp rose from the desert floor, barracks for 200 personnel, laboratories for final assembly work, communication centers to coordinate with Los Alamos and Washington. The contrast was surreal. Modern scientific equipment surrounded by Joshua trees and tumbleweeds, precision instruments calibrated to measure the birth of the atomic age in a landscape that had remained unchanged for millennia. The heart of our operation was the tower, 100 feet of steel scaffolding rising from the desert floor, designed to hold our weapon at the optimum height for maximum destructive effect. The engineers who built it worked with unusual precision,
knowing that everything within several hundred yards would be utterly destroyed. They constructed observation bunkers at distances of 6 miles and 10 miles from ground zero, concrete structures designed to protect scientific personnel and recording equipment from the blast.
As spring progressed into summer, our temporary city grew increasingly tense. The weather reports arriving daily at base camp became our obsession.
Nuclear explosions create enormous amounts of radioactive material, and wind direction would determine where that contamination would settle. We needed calm conditions, preferably with light winds carrying any fallout away from populated areas. The meteorological data from those weeks tells a story of mounting anxiety as weather patterns refused to cooperate.
My own relationship with this place evolved as we prepared for the test. Initially, the desert had seemed like a convenient laboratory, remote and expendable. But spending weeks there, watching sunrises paint the distant mountains in subtle colors, observing how life persisted even in this harsh environment,
I began to feel something approaching affection for the Jornada del Muerto. We were planning to scar this ancient landscape permanently, to introduce radioactivity that would persist for thousands of years.
The assembly building, located 2 miles south of ground zero, became the focus of our final preparations. Here we would put together the components that had been manufactured at facilities across the country. The plutonium core from Hanford, the explosive lenses from various contractors, the intricate timing mechanisms that would coordinate the implosion. The building itself was unremarkable concrete block construction, suitable for work that required precision but not permanence. Yet inside, we were assembling the most complex and destructive device ever created by human beings. Security at the site was unlike anything I had experienced. Armed guards patrolled the perimeter constantly. Radio communications were strictly controlled and heavily encrypted. Every person entering the area required multiple levels of clearance and identification. The FBI maintained surveillance on nearby communities, watching for any signs that our activities had been discovered.
We lived in a bubble of secrecy that insulated us from the outside world, but also intensified the pressure of what we were attempting.
The final weeks brought weather concerns that nearly derailed the entire operation. The meteorological reports for mid-July showed a pattern of thunderstorms and unpredictable wind conditions.
For days we debated postponement, knowing that President Truman was waiting at the Potsdam Conference for news of our success or failure. The political pressure to proceed was enormous, but the scientific risks of testing during adverse weather conditions were equally significant. I spent many evenings during those final weeks walking alone through the desert, trying to come to terms with what would happen here.
The night sky above the Jornada del Muerto was spectacular.
No light pollution for hundreds of miles meant that stars appeared with a clarity and intensity impossible to see from cities or even small towns. Looking up at those ancient points of light, I reflected on the fact that we were preparing to recreate for a few microseconds the nuclear processes that powered those distant suns. The contrast between the cosmic scale of stellar fusion and our small terrestrial experiment seemed almost absurd. Yet we were crossing a threshold that connected our species to the fundamental forces that govern the universe. For billions of years, nuclear fusion had been confined to stellar cores and the hearts of distant galaxies. In a few days, we would bring that fire to Earth, demonstrating that humans had acquired the knowledge to manipulate matter at its most basic level. The desert that had once seemed empty now felt charged with potential energy, as if the landscape itself was holding its breath in anticipation of what was coming. The ancient silence of the Jornada del Muerto would soon be broken by the most violent sound ever produced by human technology, followed by a different kind of silence, the hush that follows when history pivots on a single moment.
I often thought about the ranchers who had been displaced to create our test site. Most were Hispanic families who had worked this land for generations, running cattle on ranges their grandfathers had established.
The government had exercised eminent domain, offering compensation and relocating these families with minimal explanation. They had no idea their ancestral grazing lands would become the birthplace of the atomic age.
Their quiet displacement was one of many moral complexities that weighed on my conscience as the test date approached. The scientific instrumentation we installed across the site represented the most sophisticated measurement systems ever deployed in a single experiment. High-speed cameras positioned miles away would capture the explosion's development. Seismographs would record the Earth's response to this unprecedented shock. Radiation detectors would monitor the dispersal of radioactive materials. Spectrographic equipment would analyze the light emitted during the explosion, providing data about the nuclear processes occurring in those crucial microseconds.
Yet for all our careful preparation, we remained uncertain about fundamental aspects of what would happen. Would the explosion achieve the predicted yield, or would some unforeseen factor reduce its effectiveness?
Would the fireball behave according to our theoretical models, or would it exhibit unexpected characteristics? Would the radioactive contamination remain within acceptable limits, or would adverse wind conditions create a public health catastrophe? These questions haunted our final preparations. We had constructed the most comprehensive scientific experiment in human history, but we were also conducting that experiment with forces we had never before unleashed. The margin between success and disaster felt uncomfortably narrow as July 16th approached, and the weight of uncertainty pressed down on all of us working in that remote desert laboratory. The plutonium core arrived at Trinity site on July 12th, 1945, transported in a specially designed container that looked deceptively ordinary, a gray metal cylinder that could have contained industrial equipment or scientific instruments. But inside that unremarkable shell lay 13 pounds of the most dangerous material ever refined by human beings, plutonium-239, produced in the nuclear reactors at Hanford, Washington, represented years of the most sophisticated industrial chemistry ever attempted. Each gram had cost more than gold, and the entire core contained enough radioactive material to poison thousands of people if improperly handled. I had seen plutonium samples before, in small quantities at Los Alamos, but holding the complete core for our weapon was a different experience entirely. The metal felt warm to the touch, heated by its own radioactive decay. It emitted a faint blue glow in darkness, a beautiful and unsettling reminder of the atomic forces contained within. This material had not existed in any significant quantity anywhere in the universe until we created it. We had literally manufactured a new element, and now we were preparing to use it as the heart of an unprecedented weapon. The assembly process required extraordinary precision. The plutonium core would be surrounded by a shell of conventional explosive, arranged in precise geometric patterns. These explosive lenses had to detonate simultaneously to within fractions of a microsecond, creating a perfectly symmetrical shock wave that would compress the plutonium to supercritical density before the chain reaction could blow the assembly apart. Any asymmetry in the compression would cause the weapon to fizzle, releasing only a fraction of its potential energy. We worked in the assembly building under conditions of absolute secrecy and security. Armed guards surrounded the facility. No one entered without multiple levels of clearance. The plutonium itself was handled with instruments designed to minimize direct contact, though we understood far less about radiation exposure in 1945 than we would learn in subsequent years. The procedures we followed seemed adequate at the time, but I would later realize we were taking risks with our health that we did not fully comprehend. The explosive lenses themselves represented a triumph of precision engineering. Each lens was shaped to focus the shock wave from conventional explosives into a converging pattern that would compress the plutonium uniformly. The mathematics of shock wave propagation in 3 dimensions had never been attempted on this scale before. We were applying theoretical hydrodynamics to create the most complex explosive device ever built, relying on calculations that had never been tested under actual conditions. The timing mechanisms presented equally challenging problems. The electrical circuits that would trigger the explosive lenses had to be accurate to within microseconds, while withstanding the enormous electromagnetic pulses generated by the explosion itself. We tested these circuits repeatedly, but always with small-scale mock-ups that could not replicate the conditions they would face during the actual detonation. We were extrapolating from limited data, hoping our engineering would prove adequate when subjected to forces no human technology had ever encountered. As we assembled the weapon, we called it simply the gadget. I was struck by how ordinary the work seemed despite its extraordinary purpose. The technicians who installed the explosive lenses followed careful procedures that resembled any precision manufacturing process. The physicists who calibrated the timing circuits worked with oscilloscopes and voltmeters that looked like standard laboratory equipment, yet we were building something that would release energy equivalent to 20,000 tons of TNT in a few microseconds. The final assembly took place during the night of July 15th. We worked by artificial light in the concrete assembly building, surrounded by instruments and equipment that would measure every aspect of the weapon's performance. The plutonium core was inserted into its shell of explosives, with movements that were careful but not ceremonial. This was scientific work, not a ritual, though the implications of what we were doing gave every action profound significance. The completed device was larger than I had expected from our drawings and models.
The gadget measured roughly 5 feet in diameter and weighed nearly 5 tons. Its surface was covered with cables and diagnostic equipment that would monitor the explosion during its first few microseconds. The overall appearance was industrial rather than military. It looked more like a piece of experimental scientific apparatus than a weapon of war, which in many ways it was.
Transport to the tower required extraordinary care. The gadget was loaded onto a specially designed trailer and moved the 2 miles from the assembly building to ground zero during the early morning hours of July 16th.
I accompanied this convoy, watching as our creation crossed the desert landscape that would soon be transformed by forces we had spent 3 years learning to control. The movement was slow and careful, with frequent stops to check that nothing had shifted during transport.
Hoisting the device to the top of the 100-foot tower required precise coordination between our technical team and military personnel trained in handling heavy equipment.
The gadget was lifted by cables and pulleys, rising against the pre-dawn sky like some technological totem erected to commemorate humanity's mastery over atomic forces.
Watching it ascend, I felt a mixture of pride in our technical achievement and apprehension about what would follow.
The final connections were made as false dawn began to lighten the eastern horizon. Cables carrying electrical signals from the timing circuits snaked down from the tower to recording equipment positioned thousands of yards away. Everything we had learned about nuclear physics, everything we had calculated about explosive compression, everything we had built during 3 years of the most intensive scientific effort in human history, now hung 100 feet above the New Mexico desert, waiting for a signal that would demonstrate whether we had succeeded in harnessing the fundamental forces that power the stars. Looking up at the gadget silhouetted against the lightening sky, I realized that within a few hours, this device would either vindicate our theoretical understanding of nuclear physics or reveal fatal flaws in our calculations. There would be no partial success, no opportunity for adjustment. Either our weapon would work as predicted, or it would fail completely. The months of preparation, the years of research, the enormous financial investment, the hopes of political and military leaders, all of it, now depended on whether our understanding of atomic physics would prove correct when tested against reality. The weight of that moment was almost overwhelming. We had created something that had never existed before, assembled it according to principles that had never been tested on this scale, and prepared to unleash forces that would either confirm our mastery of nuclear physics or demonstrate the limits of human understanding. Standing beneath that tower in the growing light of dawn, I understood that we were about to cross a threshold from which there would be no return. The technical challenges we had overcome to reach this point seemed almost impossible in retrospect. The plutonium production alone had required building entire cities in Washington and Tennessee, employing tens of thousands of workers who had no idea what they were manufacturing. The theoretical calculations had pushed the boundaries of mathematics and physics. The engineering had demanded precision that exceeded anything previously attempted in human history. Yet now all of that effort, all of that accumulated knowledge, all of those careful calculations came down to a single test of a single device in the pre-dawn darkness of a New Mexico desert. If the gadget failed to detonate, years of work would be wasted. If it detonated but with insufficient yield, the weapon would be militarily useless. If it worked as designed, we would have fundamentally altered the nature of warfare and perhaps human civilization itself. As the final preparations continued around me, I found myself thinking about the plutonium core at the heart of our weapon. That 13 pounds of artificial element represented humanity's first large-scale manipulation of nuclear forces. We had reached into the fundamental structure of matter itself and rearranged it according to our will. The implications of that achievement extended far beyond military applications. At 5 hours, 29 minutes, and 45 seconds on the morning of the 16th of July, 1945, I experienced the exact moment when theoretical physics became terrible reality. I was lying face down in a trench 10,000 yards from ground zero, wearing dark glasses and holding a piece of welder's glass over my eyes for additional protection. Around me, 30 other observers lay in similar positions, scientists, military officers, a few government officials who had insisted on witnessing this moment despite the obvious risks. We had been warned to turn away from the tower, to protect our eyes from light that our calculations predicted would be brighter than the sun. The countdown reached zero with mechanical precision. "Now," said the voice over the radio from the control bunker. For the first 2 seconds, nothing happened that I could perceive through my protective eyewear. Then the welder's glass in my hand became useless against the light that erupted behind me. Even lying face down, eyes closed, covered by dark glasses and welding filters, I could see my hand as clearly as if I were holding it under a strong lamp. The light penetrated through layers of protection that should have been more than adequate for any conventional explosion. I had spent 3 years calculating the energy release of nuclear fission, but no amount of mathematics had prepared me for this. The light was not simply bright. It was an illumination unlike anything that exists in normal human experience. It was light without heat initially, pure electromagnetic energy radiating across the spectrum from gamma rays to visible photons. For those first moments, Trinity burned brighter than the sun, casting shadows that would be permanently etched into the desert floor. The silence was more unnerving than the light. Our calculations had predicted an enormous explosion, but explosions make noise, and for those first seconds there was no sound at all. The light arrived at the speed of light, 186,000 miles per second, but the sound would take much longer to cross the 10,000 yards between the explosion and our observation point. In that gap between light and sound, I experienced the most profound silence of my life. Then the heat arrived. Even at our distance, even with the protection of trenches and barriers, I felt warmth on my back as if I were lying too close to a large fire. The infrared radiation from the nuclear explosion was intense enough to ignite paper at distances measured in miles. I realized that anyone significantly closer would have been killed instantly by thermal radiation alone before the shockwave or radiation could reach them. When I finally turned to look toward ground zero, the fireball was still expanding, still climbing toward the sky. It began as a brilliant white sphere, almost too bright to observe even through protective filters. As it rose and cooled, it changed colors, white to yellow to orange to red, like watching the birth of a star in time-lapse photography. The sphere grew larger than I'd expected from our calculations, swelling to encompass what seemed like miles of desert landscape. The mushroom cloud formed as the fireball exhausted its upward momentum and began to spread horizontally against atmospheric pressure layers. This was the image that would become iconic of nuclear weapons, the distinctive shape that results when a column of superheated gas rises rapidly through the atmosphere and encounters thermal barriers that cause it to spread outward. But witnessing this formation in person, watching it develop from a point of light to a towering column that reached toward the stratosphere, was profoundly different from seeing photographs. The cloud itself was beautiful and terrible. As it climbed, it caught the early morning sunlight and displayed colors I had never seen before, purples and oranges and deep reds that seemed to glow from within. The interior of the cloud was illuminated by residual energy from the explosion, creating patterns of light and shadow that shifted constantly as the mass of radioactive gases continued to rise and spread. 43 seconds after the light, the sound finally reached us. It was not the sharp crack of conventional explosives, but a deep, sustained roar that seemed to come from the earth itself. The shockwave arrived with the sound, a pressure front that knocked several observers to the ground despite our distance and preparation. I felt it as a physical blow to my chest, a compression that briefly made breathing difficult. The sound continued for nearly 2 minutes as echoes bounced back and forth between the mountain ranges surrounding our test site. Enrico Fermi, lying in the trench near me, had prepared a simple experiment to measure the explosion's strength. As the shock wave passed, he released small pieces of paper and observed how far they were displaced by the blast. His informal measurement suggested an explosion equivalent to about 10,000 tons of TNT, somewhat less than our theoretical prediction, but still beyond anything previously achieved by human technology. The ground beneath us vibrated with a sustained tremor that lasted for several minutes after the initial shock. Seismographs as far away as El Paso and Albuquerque would record this earthquake-like disturbance, the first time human activity had created seismic waves detectable at such distances. We had literally moved the earth, displaced thousands of tons of soil and rock, created a crater that would remain visible for decades. As the immediate effects subsided and we began to process what we had witnessed, I found myself thinking of the verse from the Bhagavad Gita that had often come to mind during the Manhattan Project. Now I am become death, destroyer of worlds. The words seemed inadequate to capture what I had just experienced. Yet no other language seemed appropriate for describing the moment when human beings first demonstrated the ability to access the forces that power the universe. The tower that had held our device was simply gone, vaporized so completely that we found no recognizable fragments. Where it had stood, a shallow crater marked the point where nuclear fire had touched the earth.
The sand around ground zero had been transformed into a green glass that we would later call trinitite ordinary quartz, melted and reformed by temperatures that briefly exceeded those found in stellar cores. Looking across that transformed landscape, I realized that we had crossed a threshold that could never be uncrossed. The knowledge we had gained, the capability we had demonstrated, the forces we had unleashed, all of it was now part of human understanding and human power.
The genie, as I would later tell President Truman, was out of the bottle, and there would be no putting it back. The silence that followed the explosion was different from the silence that had preceded it. Before Trinity, the desert quiet had been the absence of human activity.
After Trinity, the silence carried the weight of knowledge that everything had changed. We had succeeded beyond our most optimistic predictions, and that success terrified me more than any possible failure could have. In the minutes following the explosion, as we began to emerge from our protective positions, the magnitude of what we had accomplished became increasingly clear. The mushroom cloud continued to rise, reaching heights that exceeded 40,000 feet before finally beginning to dissipate in the upper atmosphere.
Radioactive particles were being carried by high-altitude winds in directions we could only estimate, spreading contamination across distances that our pre-test calculations had not fully anticipated. Kenneth Bainbridge, the physicist who had directed the technical aspects of the test, approached me as we watched the lingering effects of our explosion. His face reflected the same mixture of triumph and horror that I felt. "Now we are all sons of bitches," he said quietly. His words captured something that our scientific vocabulary had no terms for, the realization that we had fundamentally altered our relationship with the physical world and with each other.
The immediate aftermath was a blur of scientific measurements and military assessments, but I found myself struggling to process the emotional reality of what we had witnessed.
We had created a piece of the sun on Earth, demonstrated that human beings could manipulate the fundamental forces that govern stellar fusion. The implications stretched far beyond warfare into questions about humanity's place in the universe and our responsibility for the knowledge we had acquired. The security badge that identified me as scientific director of the Los Alamos laboratory had seemed like a simple administrative necessity when I first clipped it to my shirt in 1943. By the time I removed it for the final time years later, that piece of laminated cardboard had become a symbol of the most consequential transformation in human history. The badge marked me as one of the architects of the atomic age, someone who had participated directly in humanity's acquisition of stellar forces, and who would bear responsibility for the consequences of that knowledge for the rest of my life. The immediate aftermath of Trinity had been dominated by military preparations and political calculations, but the deeper implications of what we had achieved became clearer as months and years passed. We had not simply created a more powerful weapon, we had fundamentally altered the relationship between human civilization and the physical forces that govern the universe.
The nuclear energy that powered the stars had become subject to human control, creating possibilities for both unprecedented destruction and unlimited constructive applications.
The attacks on Hiroshima and Nagasaki in August 1945 demonstrated the devastating potential of nuclear weapons with a clarity that no theoretical calculation could have provided. The photographs and reports from those cities revealed destruction on a scale that exceeded even our most pessimistic estimates. Entire urban areas had been obliterated in seconds, leaving behind landscapes that resembled the surface of the moon more than human habitations. The radiation effects that we had documented at Trinity translated into tens of thousands of delayed casualties among survivors of the initial blasts. Yet the immediate strategic objective had been achieved. Japan surrendered within days of the second atomic attack, ending World War II without the massive casualties that conventional invasion would have required. The moral calculus remained ambiguous. Nuclear weapons had killed hundreds of thousands of people, but they had potentially saved millions more lives that would have been lost in continued conventional warfare. The ethical implications of this trade-off would be debated for decades without reaching any consensus about whether atomic weapons represented a moral advance or a catastrophic step backward in human civilization. The personal cost of carrying this knowledge became apparent only gradually. I had entered the Manhattan Project as a theoretical physicist, fascinated by the fundamental laws governing atomic structure. Trinity had transformed me into something unprecedented in human history, a scientist who had created weapons capable of destroying civilization itself. The intellectual satisfaction of solving extraordinarily complex problems in nuclear physics was permanently overshadowed by awareness of how that knowledge could be applied. The security restrictions that had governed wartime research gradually relaxed, allowing broader discussion of nuclear technology and its implications. But public understanding of atomic weapons remained superficial, focused on their dramatic military applications rather than their deeper significance for human civilization. Most people understood that nuclear weapons were unprecedentedly powerful, but few grasped the revolutionary nature of humanity's new relationship with fundamental physical forces. The scientific community struggled to come to terms with its own role in creating nuclear weapons.
Many physicists who had contributed to the Manhattan Project expressed regret about their participation, arguing that they had been motivated by fear of Nazi atomic weapons rather than aggressive intentions.
Others contended that nuclear technology was inevitable, given the trajectory of 20th century physics, and that American development of atomic weapons had been preferable to leaving such capabilities in the hands of totalitarian regimes.
The dual nature of nuclear technology, its potential for both creative and destructive applications, became increasingly apparent as peaceful uses of atomic energy were explored. Nuclear power plants could provide electricity for cities. Nuclear propulsion could power ships and submarines. Nuclear medicine could treat diseases that had been incurable throughout human history.
The same understanding of nuclear physics that had created weapons of unprecedented destruction also offered solutions to energy and medical problems that could enhance human welfare on a global scale.
Yet the constructive applications of nuclear technology remained overshadowed by their military implications. The arms race that developed between the United States and Soviet Union created arsenals capable of destroying human civilization within hours.
The strategic doctrine of mutual assured destruction acknowledged that nuclear weapons had made total war too catastrophic for any nation to survive, but this recognition provided only fragile protection against accidental or intentional nuclear conflict.
The proliferation of nuclear weapons to additional nations multiplied the risks of nuclear warfare while diluting the ability of any single power to control atomic technology.
The scientific principles underlying nuclear weapons could not be kept secret indefinitely. Other countries would inevitably develop their own atomic weapons based on knowledge that had become part of human understanding.
The temporary American monopoly on nuclear technology gave way to a world where multiple powers possessed the capability for mutual annihilation.
The environmental consequences of nuclear testing became apparent as atmospheric detonations dispersed radioactive contamination across global ecosystems.
The fallout from hundreds of nuclear tests affected plant and animal life in ways that had never been anticipated by weapons designers. The long-term health effects of radiation exposure created casualties that extended far beyond the immediate targets of nuclear testing, raising questions about the moral justification for developing ever more powerful weapons.
The psychological impact of living in a nuclear world proved as significant as the immediate strategic implications.
Children growing up after 1945 faced the possibility that human civilization could be destroyed within their lifetimes through nuclear warfare. The existential anxiety created by nuclear weapons influenced art, literature, philosophy, and popular culture in ways that reflected humanity's struggle to comprehend its new relationship with ultimate destructive power.
The responsibility for creating this situation weighed heavily on everyone who had participated in nuclear weapons development, but it fell most directly on those of us who had directed the scientific effort.
We had solved the fundamental physics problems that made atomic weapons possible,
designed the engineering systems that translated theoretical knowledge into practical weapons,
and proven through testing that our designs would work as predicted. The subsequent use of nuclear technology for both military and peaceful purposes was based on capabilities that we had created. The isolation I experienced as one of the few people who fully understood both the technical details and strategic implications of nuclear weapons was profound and enduring.
The knowledge I carried about atomic technology could not be shared freely, even after security restrictions were relaxed, because such information remained potentially dangerous in the wrong hands.
The burden of understanding how easily human civilization could be destroyed was one that could be fully shared only with others who possessed similar technical knowledge.
The transformation of human civilization that began with Trinity extended far beyond military applications to fundamental questions about humanity's relationship with nature and technology. We had demonstrated that human beings possess the knowledge and capability to manipulate matter at its most basic level, to access energies that had previously been confined to stellar cores,
to create and control forces that could either enhance human welfare or destroy it entirely. The atomic age was not simply a period of more powerful weapons. It was an era in which human beings had acquired godlike powers over the fundamental forces that govern the physical world. The legacy of Trinity would persist long after everyone who witnessed the first nuclear explosion had died. The knowledge we gained about nuclear physics could never be unlearned or forgotten. The weapons we created established precedents for destructive capability that would influence military planning and international relations indefinitely.
The peaceful applications of nuclear technology would provide benefits that could enhance human civilization for centuries.
The environmental contamination from nuclear testing would persist in global ecosystems for thousands of years. The psychological transformation of living in a nuclear world would shape human consciousness in ways that might never be reversed.
Standing again in my memory at the edge of that desert crater created by our first nuclear explosion, I understand now that the 16th of July, 1945,
marked the end of one phase of human history and the beginning of another. Before Trinity, human beings were subject to natural forces that they could observe and occasionally harness, but never fundamentally control.
After Trinity, human beings possessed the power to create and direct forces that rivaled those governing stars and galaxies.
We had acquired knowledge that made us responsible for the survival or destruction of our own species, and possibly all life on Earth. That responsibility, awesome and terrifying in equal measure, would define the human condition for as long as our civilization endures. The silence that followed our first nuclear explosion was different from any silence that had existed before in human history. It was not the absence of sound, but the presence of knowledge that changed everything. In that moment of perfect quiet before the shock wave reached our observation point, I understood that we had crossed a threshold from which humanity could never retreat. The nuclear fire we had kindled in the New Mexico desert would burn in human consciousness forever, a reminder of both our greatest scientific achievement and our most sobering responsibility. The equations that had guided our work remained unchanged. The laws of physics that govern nuclear reactions are as constant as the speed of light or the charge of an electron. But the application of those equations to human purposes had fundamentally altered what it means to be human in the universe. We were no longer merely observers of cosmic forces, but wielders of them,
possessing knowledge that connected us directly to the nuclear processes that power the stars and create the elements from which planets and life itself are constructed.
The weight of that knowledge continues to influence every decision made by nations that possess nuclear weapons, every calculation of strategic balance, every assessment of what conflicts are worth fighting and which must be avoided at any cost. The shadow cast by Trinity extends across decades and continents, shaping the destiny of a species that must now live forever with the knowledge of how easily civilization can be destroyed and how carefully it must be preserved.